Okay, so anyone who has been diving underwater knows that as you get deeper, the pressure goes up. You can feel it in your ears. It begins to become painful if you go deep enough. To understand why, let's think about this stack of books here. Now I've got these 6 books, and if I take some sort of pressure-sensitive device, like my fingertip, and I put it between the first and second books, I can feel that. It feels like a little squeezing. Okay? I can feel the force that's pushing down on my finger from the top book. If I put that same finger between the second and third books, I can feel more of a squeeze. The force seems to go up. Now we could measure that force if we had a force-sensitive device of some kind that could record it. But if I go deeper and deeper and deeper into this stack of books, then my finger is going to be supporting more and more and more of the weight of this stack. See where I'm going with this? If I go all the way down to the very bottom and lift it up, that becomes uncomfortable pretty quickly. And so down here at the bottom, my finger is supporting 6 times as much weight as it was supporting here at the top. Okay? And so since the area of this book at the top is the same all the way down that stack, it's reasonably easy to conclude that the pressure is increasing as we go down. Because the force is going up, I can feel that, and the area stays the same, and since pressure is force divided by area, well, that means the pressure must be increasing. The numerator goes up while the denominator stays the same. So, what does that have to do with fluids? If we go to a water column, we start here at the very top of the column, and that water right there is not supporting any other water. It's just right there at the very top. But as we go deeper and deeper into that column of water, we're supporting more and more of the water that's above it. So down here, if I pick a spot right there, then I'm supporting the amount of water that is above this point. All of that water needs to be supported. It has mass, and on Earth, because it has mass, it has weight. And that weight is a force pulling straight down. Since it is not accelerating straight down, I can conclude that it must be in equilibrium, which means there must be an upward force that exactly balances out the downward pull from gravity. It's just like Newton's laws. And so from that, I can conclude that the force provided by the water at this point upward must be exactly equal to the weight of the water that's being supported. As I get further and further down, that force upward to support the water increases because there's more and more water to support. More water means more weight means more force means more, you guessed it, pressure. More weight above you means more pressure because the water at this level has to support all of that water above it. Now, what factors might affect this amount of pressure? Well, you might conclude how much water. We just talked about that. The deeper you go, the more water you're supporting, which means the greater the force, which means the greater the pressure. And so depth underneath the surface of the water, clearly that's going to have a big impact. But what about the fluid you're talking about? If I took all of this water out and replaced it with, say, honey, would that be different? Would I have a different pressure as I go down? Sure. What if I replaced it with mercury? That'd be great and fun, but it would also be significantly heavier because mercury is significantly denser than water. If I replace it with air, I'm also going to see an increase in pressure as I go down, but it's much, much less because air is much, much less dense than water is. So the type of fluid we're talking about, the density of that fluid, that plays a big role. Great. Any other factors? We've got depth, we've got density of the fluid. One of those questions I always like asking myself when I get to a point like this, what factors might affect it, is I always ask, what if I went to the moon? What if I took this column of water to the moon and I measured the pressures there? Well, if I did that, then I would know that the certain amount of water I'm talking about here on Earth weighs less on the moon because the moon has a lower pull of gravity. The gravitational field strength at the surface of the moon, lowercase g, is less than it is here on Earth. And so therefore, if I took this water column to the moon, then it would weigh less, which means that the force provided by the water at some point upward to balance out the pull from gravity would be less. And since that force is less and the area is the same, that means the pressure would be less. So the amount of pressure that I experience does depend on where I am in the universe, that local gravitational field strength. So we've got the density of the fluid, the local gravitational field strength, and the depth into which you've gone into that fluid below the surface. Anything else? What about the pressure at the top? Because right now we're just talking about the pressure down at the bottom, which is supporting the water above it, the example we gave. But here at the top, I said that the water wasn't supporting anything. And that's not strictly true, because the water here at the top is actually supporting all the air above it. That 100+ kilometers of atmosphere that's sticking out above the top of that tube. And that's not a lot of weight, but it's some. In fact, it actually is quite a bit of weight. It's about 100,000 newtons of weight for every square meter. So take a meter on a square side. There are 100,000 newtons of air above that square meter. Now, I weigh about 1,000 newtons, and so that means there's 100 of me packed into every square meter. And that's the amount of weight that is supported by the ground, or you, or this column of water, or this stack of books. That's the air pressure that we walk around in every day. That's standard air pressure, about 100,000 newtons per square meter, or what we call 100,000 Pascal, or since we like the SI system, 100 kilopascal. Okay? So the pressure that I experience lower in this water column is going to depend on the pressure at the top, because if I did this in vacuum, it may be different. The top water here doesn't have to support all the weight of air if I'm doing this in vacuum. It would also boil, but that's a different story. It also depends on the depth that you go in the fluid. It depends on the type of fluid, its density, and it depends on where you are in the universe, that lowercase g. So those four factors all roll into one and allow us to create a mathematical model for pressure as a function of depth. We can test that, we can measure it, and we can make predictions and deepen and enriching our understanding. Thank you.